In this deep dive, we will talk about a survey paper of multimodal reasoning models.
That's right. We're looking at how AI is moving beyond just text.
Exactly. Imagine AI that doesn't just read words, but actually understands the world using images, videos, sounds, reasoning across all of them.
It's a fascinating evolution.
We're diving deep into how these systems are developing. Think about an AI watching a really complex scene. It wouldn't just describe it.
No, it would grasp the why behind it, maybe even predict what happens next.
That's the goal, right? The realm of multimodal reasoning models. So today we're tracing their journey.
From the early ideas right up to the bleeding edge research, we're drawing heavily on a really comprehensive survey paper that maps this all out.
We'll unpack the different stages, the main approaches, and maybe even peek into what's coming next.
It's a really exciting space, and, the need for this is fundamental.
How so? Why the big push beyond text?
Well, traditionally, AI often focused on one thing at a time, right? Single modalities. You had your language models for text.
And computer vision systems for images, yeah? Separate worlds almost?
Almost. But the real world isn't like that, is it? It's this constant stream of information, visual, auditory, textual.
Everything hitting as at once.
Exactly. So for AI to get a truly deep kind of human-like understanding, it has to integrate all these different streams.
Makes sense. You can't understand a movie just by reading the script or just by watching the silent picture.
Precisely. And this survey paper, it does a great job of giving that broad view. Previous work might have focused maybe just on multimodal large language models, or maybe just language-centric reasoning.
But this one zooms out.
It does. It gives a wider perspective. And importantly, it really digs into the role of reinforcement learning, which is becoming crucial, and looks towards these more integrated future models.
So the aim is to build a sort of map, understand where we've been and where we're heading with multimodal reasoning.
That's the core mission, yeah. A coherent framework for it all.
Okay, let's get into this evolution then. The survey paints a picture of, well, a clear path, it seems, moving towards systems that are more unified, more adaptive.
Definitely. A trajectory towards AI that can handle high-level reasoning natively, you could say.
Moving away from just stitching separate parts together.
Right, away from those modular perception-first systems.
Towards what the paper calls native large multimodal reasoning models, NLMRMs. Sounds ambitious.
It is. But let's start at the beginning. Stage 1, as they define it.
Okay, stage 1. What was that about?
They call it perception-driven modular reasoning. So think early days. The main approach was building separate, specialized modules.
Like one box for images, one box for text?
Pretty much task-specific modules. One might use, say, long short-term memory networks, LSTMs for text.
Right, good for sequences.
And maybe convolutional neural networks, CNNs for images. Very effective for visual features.
So LSTMs and CNNs.
Got it. And you'd use these for tasks like visual question answering, VQA, answering questions about an image, or video QA for videos.
And these modules would just output their results.
And then you'd combine those outputs somehow. These early designs often had things like attention mechanisms, so the model could focus on relevant parts.
Like focusing on the dog in the image if the question's about the dog.
Exactly. And memory components, too, to help with reasoning specific to that task. Fine-grained reasoning, they called it.
But still quite separate fundamentally.
Yes, fundamentally modular.
And I guess that modularity has limits, right? For true integration.
It does. Which brings us to a major turning point, the transformer architecture.
Ah, the transformer. It pops up everywhere in AI.
It really does. It enabled much better integration of different modalities, things like pre-training on huge data sets, then fine-tuning for specific tasks.
Yeah.
That really took off.
So the transformer allowed these vision and language parts to work together more closely.
Much more closely. This led to what are called pre-trained vision language models, or VLMs. They really advanced how visual and text info could be combined, both at the data level and, crucially, within the model architecture itself.
Okay, so transformers arrive, enabling these VLMs. Were they all built the same way?
No, the survey highlights two main paradigms that emerged within these transformer-based models. Different philosophies, really.
What were they?
The first is dual encoder contrastive reasoning.
Dual encoder, meaning two separate processing paths.
That's right. Models like Vilbert, LXMERT, and maybe the most famous one, CLIPE, that's contrastive language image pre-training. They use separate encoders for, say, images and text.
But how do they connect them?
Through contrastive learning. The core idea is to teach the model to align the representations from these separate encoders in a shared space.
So making the model understand that the picture of a cat and the word cat are related.
Exactly. Pulling related concepts together in this learned space, pushing unrelated ones apart. CLIP was famous for its zero-shot ability because of this.
Zero shot meaning it could identify things it wasn't explicitly trained on.
Yes, just by seeing if the image representation was close to a text description's representation in that shared space. Really powerful.
And other models followed this dual encoder path.
Oh, yes. RLPO, meter, SimVLM, VLMCoca, BLA. Lots of variations on this theme of aligning separate representations first.
Okay, that's one approach. What was the second main paradigm?
The second is single transformer backbone interactive reasoning.
Single backbone. So putting everything through one main transformer.
Precisely. Models like VisualBERT, Uniter, VLBERT, PixelBERT, they take a different route. They embed both the visual and textual inputs together and process them within a single unified transformer.
So the interaction happens much earlier and more deeply.
That's the idea. It allows for more direct, fine-grained interaction between modalities right from the start. Think of models like UniVL for video and language, Oscar, VinVL using object tags, ErnieVL with scene graphs.
It sounds more integrated.
Potentially, yes. More recent ones like Unit, Palai, Flamingo, BIT3, OFA, BLIP2, and the Cosmos models follow this path too. Cosmos 1, for example, could handle interleaved image and text inputs seamlessly.
So stage one, built the foundations, figured out ways to combine modalities, heavily influenced by the transformer. Got it. What happens in stage two? The survey calls it Language-Centric Short Reasoning System 1 Reasoning.
Right. This marks a significant shift. The rise of multimodal large language models, MLMs, really drove this stage.
So leveraging the power of those huge language models, but making them multimodal.
Exactly. The focus shifted from building separate perception modules to creating end-to-end systems where language acts as the central hub, the main reasoning engine.
And these MLMs, they showed promise.
They did. Strong performance on tasks like visual common sense reasoning, VCR, or visual grounding, linking text to image regions.
But there were limitations. The System 1 part of the name suggests that, like fast, intuitive thinking, but maybe not deep, deliberate thought.
That's the key insight the survey points out. Early MLMs were often good at surface-level pattern matching. They could find associations they'd seen in the data.
But struggled with multi-step logic, dynamic hypothesis generation.
Exactly. They lacked robustness in those areas. They weren't great at really thinking things through step by step.
Which is where chain of thought comes in, coati. We hear that term a lot with LLMs.
Precisely. Chain of thought reasoning became a key technique to tackle this lack of depth. The idea is to make the reasoning process explicit.
How? By making the model show its work.
Essentially, yes. Instead of just giving the final answer, you prompt or train the model to generate the intermediate steps, the chain of thought, that leads to the answer.
Making its reasoning visible, and hopefully more reliable.
More visible, more interpretable, and often more accurate. So stage 2 is largely about different ways to implement and enhance this language-centric reasoning, often using CODI. The survey breaks it down into 3 main approaches.
Okay, what's the first approach within stage 2?
The first is prompt-based multimodal chain of thought, or MSOT. This is all about clever prompt engineering.
Using the input instructions to guide the model's thinking.
Exactly. You design the prompt to lead the MLLM through a sequence of reasoning steps in the multimodal context. For instance, using scene graphs to prompt step-by-step video understanding.
Can you give another example?
Sure. Video Agent prompts the model iteratively to pull key info from long videos. Or in autonomous driving, PKRD Cote uses prompts to structure the whole perception reasoning decision loop.
So prompts are used across different domains.
Oh, yes. Empathetic response generation, emotion recognition, object detection like Code 10, action understanding, ANSI-PT, even image segmentation, CP-Seg. Careful prompting guides the reasoning.
Interesting. So the prompt itself acts like a scaffold for the model's thought process. What's the second stage 2 approach?
The second is structural reasoning. Here, you rely more on predefined structures or patterns to guide the reasoning rather than just the initial prompt.
Predefined structures. Like what?
A key part is rationale construction. Training models specifically to generate good rationales, those intermediate steps.
Focusing on the quality of the showing your work part.
Right. Multimodal COT, for example, separates rationale generation from answer prediction to try and reduce errors or hallucinations. Research like T-Psych showed rationale quality is really key.
And other structured approaches.
Well, there's G-COT for driving, linking rationales to visual data. NCUT uses self-consistency, generates multiple rationales, and picks the best one. QLT tries to get more exploratory rationales.
Are there more complex structures?
Definitely. Models like BDOG Blueprint Debate on Graph actually simulate a debate between agents to reason. CUTI-DET, for object detection, uses a list analyze summarize structure. Shikra identifies different reasoning responsibilities. ECOT integrates planning for embodied AI.
So, providing a more rigid framework for the reasoning process. Makes sense. What's the third stage 2 approach?
The third is externally augmented reasoning. This is about boosting the model's capabilities by letting it use external tools or retrieve information.
Giving the MLM superpowers, basically. Access to outside help.
Kind of, yeah. One way is search algorithm-enhanced MCOT. Using search algorithms like an MMTOT, multimodal tree of thoughts, or AGO, aggregation graph of thought, to explore different reasoning paths.
Like exploring a decision tree of thought.
Exactly, trying to find the best path to the answer. BDOG's debate format could also be seen as a type of search, exploring different arguments.
Okay, search algorithms. What other external help?
Actual external tools. L3GO uses Blender for 3D object generation. HYDRA combines reinforcement learning agents and vision models for complex QA. DETCODE uses specific visual processing prompts as tools. Some models even generate intermediate images to help with visual reasoning.
Wow, generating images to help itself think visually. That's clever.
It is, and Animal integrates diverse tools efficiently. SECMRN uses syntactic graphs for common sense reasoning.
And retrieval, getting external knowledge.
That's the other big part, retrieval augmented generation, or AG. We see this a lot now.
For fetching relevant facts or context.
Precisely. Rhagar uses it for political fact-checking. Chain of Action retrieves from diverse sources. CAMCOAT uses knowledge graphs. ARMCTS combines retrieval with Monte Carlo tree search. MRMKG uses multimodal knowledge graphs.
So pulling in relevant knowledge dynamically to make the reasoning stronger.
Exactly. There are many examples enhancing VQA with memory, using scene graphs, refining image descriptions. The core idea is augmenting the MLLM's internal knowledge and reasoning ability with outside resources.
Okay, stage 2 feels like taking those MLLMs and really trying to make them reason better using prompts, structures, or external help. Now, stage 3, Language-Centric Long Reasoning System 2, Thinking and Planning. This sounds like the next level up in complexity.
It absolutely is. Stage 3 aims for that more deliberate compositional reasoning. Think multi-step complex tasks involving explicit planning.
Like System 2 thinking in humans, slow, effortful, logical.
That's the analogy. It's about extending those reasoning chains, making sure they're really grounded in the multimodal inputs, and using supervision or reinforcement learning to train these deeper capabilities.
So what are the key areas within stage 3?
One major focus is crossmodal reasoning. This really pushes for deeper integration across modalities, beyond just combining text and images superficially.
How do they achieve that deeper integration?
Through more sophisticated use of external tools, developing algorithms to control how modality-specific steps are interleaved, and designing models with better intrinsic fusion capabilities.
Examples.
Ideal GPT uses GPT to break down and answer sub-questions about images. Assist GPT uses tools for planning and execution. ProVicQ actually generates and runs Python code to reason about videos.
Writing code to help itself reason. That's
Yeah.
impressive.
It is. NLMRMs combines vision specialists with GPT. Visual Reasoner synthesizes reasoning data. And intrinsically, models like VOCOT do visually grounded object reasoning. MVOT uses image visualization for spatial reasoning.
So really trying to get modalities to work together fluidly. What else is key in stage 3?
Another area is multimodal O1. This is inspired by models like OpenAI's O1, focusing on multi-stage structured reasoning paths.
Expanding that chain of thought idea further.
Yes, making it more structured. Instead of just thinking answer, maybe summary, rationale, captional, thinking answer, breaking it down more formally.
Which models fit here?
Macro O1, LlamaBerry, LlamaCut, LlamaV01, Mulberry, Redstar Geo. They often use search techniques like Monte Carlo tree search, MCTS, to explore these structured solution paths.
MCTS. Okay, so exploring different ways to solve the problem within that structure.
Right. It's about strategic exploration of the solution space, not just following one chain.
And the final key area for stage 3.
That would be reinforcement learning from preference optimization, or RLPO.
Using reinforcement learning based on human preferences to fine-tune the models.
Exactly. Learning what makes a good reasoning process or output based on feedback. The success of text models like DeepSeek R1 using a similar method, GRPO, really spurred this on in the multimodal space.
So models are being trained using RLPO for multimodal tasks.
Yes. Emirika, VTR1, LMMR1, R1V, VLMR1, Visual RFT, Seg0, Video R1, Video Chat R1, R1 Omni. They're applying RLPO to everything from geometry problems to visual grounding to video understanding.
But there are challenges.
A big one is generalization. It's hard to get the long-chain reasoning learned on one specific task to transfer effectively to other different tasks. That's still an open research problem.
Okay, stage 3 is really pushing towards deeper, more planned and learnable reasoning, which leads us finally to the future vision. Native Large Multimodal Reasoning Models, NLMRMs.
Yes, this is the survey's forward-looking paradigm. The big idea here is that reasoning shouldn't be bolted onto a language model. It should emerge natively from omnimodal perception and interaction.
So reasoning is a fundamental property arising from understanding all senses together, driven by goals, not just a language task.
Exactly. Moving beyond current architectures. The survey outlines 2 foundational capabilities these NLMRMs would need.
What are they?
First, multimodal agentic reasoning. Think proactive, goal-driven agents interacting with the world, decomposing tasks, adapting in real time, learning from embodied experience.
Like robots that can truly understand and act in complex environments.
That's the direction. Second, omnimodal understanding and generative reasoning. Seamless analysis and synthesis across all modalities using unified representations, fusing heterogeneous data for contextual interaction.
Seeing, hearing, talking, acting, all integrated.
That's the vision. Current models like OpenAI's O3 and O4 Mini are showing glimpses, finding locations, solving puzzles, creating multimedia, visual problem solving. But they don't fully combine these agentic and omnimodal capabilities yet. There are still limits on sustained interactive reasoning across diverse modalities.
So NLMRMs are the goal, the integrated future. What are the big hurdles to getting there? The technical challenges.
The survey points out several big ones. First, unified representations and crossmodal fusion. Building that single architecture to handle everything coherently is tough. Moving beyond separate encoders to truly deep integration.
That sounds fundamental.
It is. Then there's learning from world experience, enabling continuous lifelong learning from real-world interaction. Embodied AI, learning and simulation. That's crucial, but very hard.
And data. Is getting the right training data a challenge?
Huge challenge. Data synthesis. We need high-quality data pipelines to train these complex reasoning skills, aligning modalities, creating interactive thought chains, multi-step planning, coordinating tools. It's a massive undertaking.
Unified architectures, learning from experience, massive data needs. Definitely sounds like a long-term research program.
Absolutely. And progress relies heavily on good ways to measure capabilities.
Which brings us to the data sets and benchmarks mentioned in the survey. They seem critical for driving progress.
They're indispensable. The survey provides a really extensive list categorizing them. You have benchmarks for multimodal understanding.
Like VQA, image captioning, video understanding, audio understanding.
Right. Visual-centric, audio-centric, even multilingual and comprehensive ones like Bench. Then there's multimodal generation.
Text-to-image, text-to-video, text-to-speech.
Exactly. Cross-modal generation, joint generation. Then the really key category, multimodal reasoning.
Benchmarks specifically designed to test the kind of reasoning we've been talking about.
Yes. General visual reasoning like VQA, NLVR2, ScienceQA, MathVista, and domain-specific ones for math, science, physics, even world models and general intelligence benchmarks like MMMU and AG-EVIL.
And finally, planning benchmark.
Right. Multimodal planning, things like GUI navigation, WebArena, Mind2Web, interacting with operating systems, and embodied simulated environments like MyDojo, Habitat, RoboGen.
Wow, that's an incredible range of tasks and data sets. It really shows the breadth of what multimodal AI is trying to achieve.
It does, and these benchmarks constantly evolve, getting harder as the models get better. It's this cycle of model improvement and benchmark challenge that pushes the field forward.
So we've really covered a lot of ground, from those early modular systems focusing on perception.
Through the language-centric stages, trying to build reasoning on top of LMs using prompts, structures, external tools.
To the push for longer, more deliberate reasoning in stage 3, using things like RLPO.
And finally, looking towards that future of native, large, multimodal reasoning models, the NLMRMs, that can truly integrate sensing, reasoning, and acting.
It's clear the challenges are immense unified representations, learning from experience, data synthesis.
Significant hurdles, no doubt.
But the potential impact seems enormous.
Yeah.
If AI can truly understand and interact with the world holistically, Think about robotics, accessibility, education.
The possibilities are transformative. When AI can seamlessly blend seeing, hearing, reading, reasoning, and acting, what becomes possible?
It really does feel like we've just scratched the surface here. It's such a dynamic field. We definitely encourage you, our listener, to explore this research further.
Absolutely. Ponder that transformative power.
What aspects of this, what potential applications really capture your imagination? What comes to mind when you think about AI that can truly reason across all our senses?